And we'll get my, if I can get my screen share up here, see if I can get 9.1 loaded. All right, here is where we left off last time. Let me move some taskbars around because they tend to get smack in the way. Okay, and we'll go from current slide. Okay. All right, can everybody see limit of a sequence now? Can anyone see it? Speak to me, somebody.
Yes, sir.
Okay, good deal. All right. Just want to make sure that Zoom is working. Oh, two more people coming in. Let's see. There's Jemanuel. And here's Pullum and Jemanuel. So he's coming in as two this time, I think. He's the only Jemanuel I have. He's the only Pullum I've got. So I'm only going to mark him present once, though. So we're missing Esther and Laron. Has anyone heard from Esther? It's been a while now. Okay, well, I'm going to minimize this. And let's see. Okay, Jemanuel's here as Pullum, and he's trying to get in as Jemanuel. Has he got a duplicate here? Let's see. That should be 1, 2, 3, 4, 5, 6. Yeah. So I don't know what's going on with Jemanuel. We'll wait until he gets in and find out. Okay, Jemanuel, can you hear us yet?
Yes.
Okay. Are you coming in on two different devices? Because I have a Jemanuel here and a Pullum here.
Yeah, I was trying on my computer, but it was still saying I wouldn't let me in, so I tried on my phone.
Oh, I see. Okay. Well, I should have blocked them both. No, I'm just kidding. Okay, never mind. Okay. All righty. Any issues, concerns, problems, anything else before we get started? And it may have to do with math too. Any calculus or other related issues that you want to bring up? All right, I take that as a no. We got started last time on 9.1, which is sequences. Chapter 9 is infinite series. So we'll be first talking about sequences, and then we'll be talking about series. Now, we started last time and talked a little bit about a sequence. Now we're going to get to the limit of a sequence. Okay. And this, at times, hardly seems like calculus, but it does have very direct applications to calculus. So unfortunately, we won't be able to follow up on too many of those because we just got too much to cover. But I'll try to do a quick and dirty run through of some applications once we're through with these two topics, sequences and series. So what is the limit of a sequence? The primary focus in this chapter, though we're only going to do 2 sections of it, concerns sequences whose terms approach limiting values. Such sequences are said to converge. The sequence is said to converge. So here is an example. Here's the sequence 1 over 2n, not 1 over 2 to the nth. Okay. Now, if you remember, we can refer to a sequence in several ways. One way is to put the nth term in braces, and that's what they've done here. Here they've taken it and started listing the terms. When n is equal to 1, remember n is just a counter, and the counter usually starts at 1 and goes up by whole numbers. Okay, so when n is equal to 1, that would be 1/2. When n is equal to 2, that's 1 over 2 squared, which is 1/4. n equal 3, 1 over 2 to the third, which is 1/8. 1 over 2 into 1 over 2 to the fourth, 1/16. 1 over 2 to the fifth, 1/32, and so on. Now, looking at that sequence of numbers, obviously they're getting smaller and smaller and smaller. 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1/28. They're getting very, very, very small, and that converges to 0. Notice it doesn't go negative, and we wouldn't expect it to. Nothing's negative here, so there's no way it could. So it's getting smaller and smaller and smaller. Must be going, in this case, to 0. So here's the definition that tells you indeed that does converge, that it does have a limit. Let L be a real number. That's a very distinct phrase, isn't it? The limit of a sequence. Now, is this little box here blocking your view? It is mine. Yes. Okay. It's going to fade out in just a few minutes. There it goes. The limit of a sequence, there's your braces, a sub n, is L, written this way. The limit as n approaches infinity, n's getting larger and larger and larger, of a sub n is equal to L, if for every epsilon greater than 0, oh boy, this sounds like a good old limits on derivatives, doesn't it? For every epsilon greater than 0, there exists some capital letter m. I think we were on this slide last time. That's also greater than 0, such that if the difference between the a sub n here, that's that ith entry here, and the limit L is less than epsilon, that small small positive number here, whenever n is greater than that m that you picked, then that limit exists. If the limit L of a sequence exists, then the sequence converges to L. If the limit of the sequence does not exist, then the sequence diverges. Now, diverging doesn't mean it gets huge, it just means it doesn't converge. Okay, so you usually think of diverging as in further and further apart. Here it just means it doesn't get closer and closer together. It doesn't converge. Okay, that's what diverging means here. Graphically, that definition says that for all n greater than that value m, it seems like we did this one before, didn't we? Did I mark the wrong place? No, I don't think so. Okay, I've taught this so many times it seems like I've seen it before. Okay, this definition that eventually for n greater than m and epsilon greater than 0, the terms of the sequence will converge to L, will lie between a band that's between y is equal to L plus epsilon and y is equal to L minus epsilon. So if your sequence starts up here and then goes down here and then goes up here and then down here and goes up here, down here, that is sort of bouncing around. No real clear illustration or indication this is going to converge. But then it goes up here. Notice it's deviating less every time, then goes down here and then here. But once it gets past that point right there, that would be m minus 1, it looks like. From then on, it stays inside this band of L. See, L is right here. This happens to be your limit. You wouldn't have known that before. And it stays between L plus epsilon, which is a little bit more than L, and L minus epsilon, just a little bit less than L. If it consistently stays in there for all n's greater than m, then it has to be converging to that value L. Okay? That's the graphical illustration of what we're talking about here. If a sequence a sub n agrees with a function at every positive integer, and f of x approaches a limit L as x approaches x approaches infinity, then the sequence must also converge to that same limit. So here's two different definitions. One, the epsilon definition for the limit itself, and then if you have a function and it has a limit as x goes to infinity, then it also. Remember, a function f of x is usually a continuous entity. When you're dealing with sequences, you're dealing with discrete entities. n equal 1, equal 2, equal 3, equal 4, equal 5. But if you had put the n in for here at x rather than n, and x, the continuous x, is approaching the limit L, and at every value, whole number value n, that also is approaching that same value, then the limit still exists for that. Okay. So here's in fact, this is, I guess, where we should have started. I'm sorry, I was on the wrong mark here. Sorry. This is where we should start. Let L be a real number, any old real number, if f is a function of a real variable x such that the limit as x approaches infinity of f of x is equal to L. Okay. If, then you also have a sub n, which is a sequence such that f of n, that same function here x was a continuous variable. You could put in any value you wanted to, 7.438251, and any value x you put in there. But here you're only putting in those integral values, 1, 2, 3, 4, 5. But if that sequence such that f of n is equal to a sub n for every positive value n, integer n, then if this is true for any old continuous x, it'll also be true for any discrete integer n as n gets going to infinity. The a sub n then is approaching L. So that's one test. If the limit of the function that agrees with the a sub n has a limit, then the sequence also has a limit. So here's example 2, bottom of page 589. Find the limit of the sequence whose nth term is a sub n is equal to 1 plus 1 over n raised to the nth power. Okay? Well, this one's a fairly interesting one. And it's sort of asking you to remember something that doesn't seem to be connected with it very well, but indeed it's true. So here's what you're doing. Let's just take a few terms of this. When n is equal to 1, this will be 1 plus 1 over 1, which is 1. 1 plus 1 is 2. Raised to the first power would be 2. Okay? When n is equal to 2, this would be 1 plus 1 half raised to the second power. So that would be a 2.25, I believe it is. That's 1.5 squared, I think is 2.25. And that's probably all I can do in my head. When n is equal to 3, that's 4/3 raised to the third power. So I'm going to pull out my handy dandy calculator for that one. Okay, I just had a message from the dean and said give her a call. I'm not going to do it now. I'll wait till after 4 when I'm through with classes. So anyway, let me get my calculator up. Sorry that took me a while, but that's what I was doing, reading the message. Okay, what does I say? 4/3. 4 divided by 3 equal, raise that to the third power. Oops, I can't do it on this screen. I could have, but it's easier to do it here. Cubed equal, not right. Something screwed up there. Let me start that one over. Okay, 4 divided by 3 equal and cube that. There we go. That's much better. That gives me 2.37 and change. 2.37 ... Okay. How about the next one? That would be 1.25. Whoa, missed the decimal there. 1.25. I've got fat fingers and small keys, and this doesn't work well. 1.25 and raise that to the fourth power, and we get 2.44 approximately. 2.44. Okay, now each of these numbers is increasing, but we don't know if it's increasing without bound, and there's really not any easy way to tell that. Let's just do a few more. At n equal 5, that would be 1.2, because 1/5 is 2, and going to raise that to the fifth power. I got 2.48, or I'm going to call it 2.49. Okay, going up, but not quite as fast as it was a while ago. See, this difference is 0.25. This is 0.8. That is 0.7. This is 0.5, 0.07, 0.05. So it's getting smaller. No guarantee this is going to converge. It could just keep getting bigger and bigger and bigger. So the next one is going to be 7/6. That's 1 plus 1/6. That would be 7 divided by 6 equal, and then raise that to the sixth power. I get 2.52. Okay, now that time, see, the difference between these is 0.05. This is 0.03. So it still seems to be decreasing. Now you could do this and do this and do this, and you probably won't be able to tell for sure that it's converging. It sure looks like it is because the difference is getting smaller, but how they suggest we do it, in fact, let me just show that so I won't have to do all the writing. And this is what they went by. And this is what I was saying. It's requiring you to know something that you probably didn't think of in this context. But this is a limit that you probably did run into a long time ago, but it wasn't in this context. The limit as x is approaching infinity of 1 over 1 plus 1 over x raised to the x power. That is exactly the definition of E. So let me pull E up here and let you see what that is. There we go. That is 2 point, and this again is an irrational number. I've got to find my, where in the world is my, there it is. Nope. No wonder I'm typing on the wrong screen. I have two pads. One's a Wacom pad and one's my finger pad, and sometimes I use the stylus on the finger pad and use my finger on the Wacom pad, so they don't work. Okay, this is approximately equal to 2.72, and it's not exact. So you see, if we had kept going and kept going and kept going, it was going to take us a long time to get here, because every difference was getting smaller and smaller and smaller, and my internet connection is unstable, so I'm going to quit talking for just a minute, and it disappeared. Did y'all get, were you able to hear me when I kept talking, or did I break up? Anybody? I was breaking up, but it's better. Is it better now? Am I still breaking up? Okay, good. Okay. I hope that was the first answer. Okay. So indeed, that is E, 2.72. So that does converge because there is a limit. As x is going to infinity, therefore as n is going to infinity, the same thing will converge to the same value. Okay. Now they just pulled that out of their ears or some other body part, and that gave, you can then conclude that theorem 9.1, that if the limit of the function is E, then the limit of the sequence is also going to be E. So that works. And that required you to recognize that form, which is not all that satisfying because sometimes there are forms I don't recognize. But that one, of course, is one that if you've been around it long enough, you will. Okay, let's move on to, I'm trying to find the, oh yeah, this is the bottom excuse me, bottom of page 589. Okay, there are different ways in which a sequence can fail to have a limit. One way is that the terms of the sequence increase without bound or decrease without bound. If either of those is happening, hey, it will fail to have a limit. See, just looking at this, these numbers we did here, they just keep increasing. We can't tell by looking at these numbers whether there's an upper limit or not. It just is not apparent. When we looked at this, we saw, yes, that has a limit, so therefore this has a limit. So yes, there is a place that it's approaching. But just looking at the sequence, and there we looked at 1, 2, 3, 4, 5, 6. I just ran out of room. We could have gone on 7, 8, 9. They would have kept increasing, but we couldn't tell if there was a limit or not. So this is saying if they just keep increasing without bound or decreasing without bound, going down, there's no limit. Those cases are written symbolically this way. The terms of increase without bound, that the limit is a sub n as n approaches infinity is infinity. And terms decreasing without bound, the limit is of a sub n as n goes to infinity is negative infinity. Now the one good thing was these back here, they were increasing, but they sure were increasing more slowly. So you had a gut feeling there may be a limit there. But gut feelings don't always hold true. Okay, so you can't always trust that. And you certainly couldn't tell just looking at this what that limit was. Okay, but if they do just increase and increase and increase and increase, yep, not going to have a limit. Or decrease, decrease. So here's theorem 9.2. This is the top of page 590. Let the limit as n approaches infinity of a sub m equal L. Now, is that somebody coming in? I keep getting these little sounds and I don't know where they come from. Let me see if anyone's waiting. I don't see anybody waiting. Okay. So, let the limit as n approaches infinity of a sub m equal L. So, we're told it does have a limit. And the limit as n approaches infinity of b sub n equals k. So, it has a limit. They've told us both of these sequences here, a sub n and b sub n, have limits. Now, here are the properties. If you have two sequences that do have limits, scalar multiple, the limit as n approaches infinity of some scalar multiple c, any real number in the world, 5,872,416 and 2/3, that's a real number, okay? And that can even be bigger, okay? But if you multiply that by a sub n, that's not going to change. It will change what the limit is, but it doesn't, no matter how big that c is, as long as it's a real number, a finite number, you can multiply it by a sequence, and that sequence, if that sequence has a limit, so does the multiplied. Even though it's an enormously large number, it'll just be that enormously large number times whatever that limit was. For c is any real number. Okay? Can also go in the other direction. Incredibly small numbers. Okay? As in negative 485 million something another. Or it could be c is an incredibly small number, as for being close to 0. It's still not going to change the fact that the limit exists. Okay? Now, what if you have a sum or difference of these two sequences? Well, those will also have a limit. Even though this may be a very large number and that a very large number, guess what? If they're just numbers, add them together, that's still just a large number. Or subtract them from one another, still just a number. So the limit of a converging sequence, or the limit of a sum or difference of two converging sequences, gives you the sum or the difference of their limits. Okay, that's what that tells you. Now this one, the product, whoa, now we're going to multiply them. Won't they get out of hand? No, they won't. The limit of two converging sequences will give you, as n approaches infinity, both of these converge, that'll just give you the product of their limits, which I hope you would expect. And the quotient, same rule. Only one exception though. The limit is n approaches infinity of a sub n divided by b sub n. As long as both of these have limits, it's going to be L over K as long as that K is not 0. If that K was 0, this limit doesn't exist because you can never divide by 0, not even in sequences and limits or anything else. The B sub n, not only can K not be 0, that's true, but B sub n can't be 0 either. So you can't be bouncing along there and every so now and then the B sub n goes to 0. Can't do it. That sequence would not exist. All right. Any questions on that? Just the basic properties of limits. If you know the two sequences have limits, then these 4 conditions are met. And now it won't advance. So I have to click on the screen and get it to advance. Here we go. Now here's maybe a new symbol for you. Okay, have y'all run into factorials before? Anybody? Oh, you have. Okay, good. What n factorial means is to simplify some of okay, the symbol n factorial, that's how you say it, is used to simplify some of these formulas. Let n be a positive integer, then n factorial is that positive integer. Now, that positive integer could be enormously large, 583. Well, what is n factorial then? 583 times 582 times 581 times 580 times blah, 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 all the way down to 1. Now they do it the other way. They start with 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8, all the way up to times 5,000, whatever I said, times finally the last number. That is what we mean by n factorial. Notice n is a positive integer. Now, 0 is not a positive integer. It's an integer, but it's neither positive or negative. But we still have to have a definition for 0 factorial, and guess what? It's not 0, it's 1. 1 factorial is 1, 0 factorial is 1. 2 factorial is 1 times 2, which is 2. So 0 factorial and 1 factorial are both 1. All the others are bigger. So from that definition, you can see that 1 factorial is 1, 0 factorial is 1, 2 factorial is 2, 3 factorial is 2 times 3 is 6, 4 factorial is 6 times 4 is 24, 5 factorial is 24 times 5, which I think is 120 maybe. 6 factorial is 6 times that, which is 720. 7 factorial would be 7 times that, which is an enormously large number. The factorials get big really, 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 really fast. Okay? So that's what we mean by factorial. They count from, start multiplying from 1s going up to n. I usually start with n's and go down to 1. Either way, multiplication is commutative and associative. Factorials follow the same conventions for order of operations as exponents. So they fall right in there. That is, just as 2x cubed, that would mean you cube the x first and then double it, double that answer. And 2x cubed, that means you multiply first and then cube it. Those are different values, okay? This would be 8 times x cubed because it's 2 cubed times x cubed. This is just 2 times x cubed. Well, the same thing applies here for factorials. 2n factorial, treat that as if it's an exponent. It's twice what n factorial is. Whereas if you did 2n factorial, you would start with 2n. Well, let's just say, give me an n, anyone. Give me an n. Any positive integer n. Give me one. Say again. 4. Excellent. This would be 2 times 4 factorial. That'd be 2 times, look at you. Oh, no, okay. 4 times 3 times 2 times 1. Well, times 1 you don't have to do. 4 times 3 times 2, that would be 24, wouldn't it? I believe so. 4 times 24 is whatever that is, 96. Okay? Now, what if it was 2 times 4? That would be 8. 8 factorial would be 8 times 7 times 6 times 5 times 4 times 3 times 2. Whoa, it's way, way bigger than 2n factorial. Just like this is way bigger than that. Okay, so 2n factorial would be 2 times 1 times 2 times 3 times 4 up to n. You chose 4, so we'd stop right there. Whereas 2n factorial would be 1 times 2 times 3 times 4 times 5 times n plus 1 times n plus 2 times n plus 3 times 2n. That would go up to 8. So it'd be 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. Okay? So this would be far, far bigger. Okay. Another useful theorem that can be rewritten. Let me make sure I'm not skipping something. Oh my goodness, I did skip something, didn't I? Yuck, I skipped a lot. Let me go back, sorry. Right here, before we even get to factorial, they skipped examples 3 and 4. So let's us do example 3. So if I can get my cursor to show up here, I'm going to do a new share. Let's see, we've still got 6 students here. Is that right? 1, 2, 3, 4, 5, 6. Got it. Okay. So let's go to the whiteboard. All right, here we go. Now I've got to do some organizing here. First, I'm going to scoot this. You can't see it, but I have a taskbar here that gets in the way. So I'm going to scoot it as far to right and up as I can. Then I'm going to scoot my whiteboard as far to the left and up as I can to give me the maximum writing space that I can have. That's about it. Okay, let's do example 3. Now, example 3, you can go to larsoncalculus.com and see an interactive version of this type of example. So, here's A. Let me see if I can write it here. Example 3A. Here is a sequence, A sub n, and the pen is doing strangely right now. I'll try to slow down. And this is equal to 3 plus a negative 1 raised to the nth. Okay. Now, firstly, we could do it brute force. Okay. Let's let n equal 1. Usually start with n equal 1. N equal 1, that'd be 3 plus negative 1 to the 1 power. Well, negative 1 to the first is negative 1. 3 plus negative 1 would be 3 minus 1 is 2. And then 3 plus negative 1 squared, that would be 1. 3 plus 1 is 4. And then 3 plus negative 1 to the third power, well, that'll be negative 1, so that goes back to being 2 again. And then the next one's going to be 4, the next one's going to be 2, the next one's going to be 4, the next one's going to be 2. Do you see the pattern here? Dot, dot, dot. Okay? Do you think that converges? Is there some number that if you get far enough out there, every one of those terms is going to get closer and closer to that number? No. Okay? Don't take an average and say 3. No, that's not going to work either, because none of them will ever be 3. And no matter how far you go out there, it'll never be 3. It'll keep going 2 to 4, 2 to 4, 2 to 4, 4 to 2, 4 to 2, 2 to 4, 4 to 2. Never converges. So like I said, converging doesn't mean it's going to explode. It just means it doesn't have a limit. Okay, now by what we learned before, here's the other way we could say that. This would be the same as saying 3 plus the limit of this, and that would be 3 plus 1, or 3 minus 1, 3 plus 1, 3 minus 1. So yeah, that's never going to converge. Okay, they don't even do that second part, they just left it. So let's go to the B part. Here's B sub n, another sequence B sub n, and its nth term, if this pen would write, its nth term would be n over 1 minus 2n. Okay, now let's see what that one would be. When n is equal to 1, you would have 1 over 1 minus 2, which would be a negative 1. So that would be a minus 1. Now you do the math too and make sure I don't make a stupid mistake. When n is equal to 2, you have 2 over 1 minus 4. So that would be a minus 2/3. Well, that's looking a little promising so far. If you do n equal 3, that would be 3 over 1 minus 6 would be a minus 5, or minus 3/5. Okay, I'll put the minus there. Okay. The next one would be a minus 4 over 7. The next one would be a minus 5 over 9. The next one would be a minus 6 over 11. The next one would be a minus 7 over 13. And you can keep doing this till the cows come home. Okay? Now, does that have a limit? Well, certainly the numbers are getting larger in a negative sense. You know, the negative 1 is less than negative 2/3, is less than negative 3/5, is less than negative 4/7, is less than this. So they do seem to be, they're increasing, but they're increasing by smaller amounts every time. So does that mean it has a limit? Well, let's see if we can, I don't want to go any further than the book does. Yeah, here's the technique that we use here. The other one, we just did it. I was wondering when they were going to get around to showing the technique. That would be the limit as n is going to infinity of n over 1 minus 2n. We're investigating that. Now here's the technique we use, and you probably have run into this before, and it's a legal move. Okay, let's divide both numerator and denominator by n. So this will be n over n over 1 over n minus 2 n over n. So I've multiplied and divided numerator and denominator by 1 over n. Okay? Legal move because n's getting bigger and bigger and bigger, so you're dividing by some large number. You're not dividing by 0. Okay. Well, what does this give us? Okay, let's take a look at that. That'd be the limit as n approaches infinity of, the numerator here becomes 1. The denominator here, 1 over n, as n gets very big, that goes to 0. This one, though, is negative 2. So our limit here is negative 1/2. And sure enough, that's what it seems to be going closer and closer to. If I had done that on my calculator, you would see that the numbers, the first one of course is a -1. Okay. So the first would just be -1. I forget on this calculator you have to enter the number first and then change its sign. The second one would be -2/3. That would be 2 divided by 3 equal, and negate that, that's -0.6, about 0.7. The next one, -3/5, that's -0.6. So you went from -1 to -0.7 to -0.6. 4/7, 4 divided by 7 equal, that's -0.6 again, but it's a smaller 0.57, about 5/7. And then 5/9 be 5 divided by 9, that's -5.55. 6/11, 6 divided by 11, that'd be -0.54. So getting closer to 0.5, not quite getting there, but getting closer. 7 divided by 13, and again you're getting closer. But if you kept this up for a long time, you're getting closer and closer to 0.5. You never really reach it, but that's where it's going to in the limit. And we've only got down to -0.54, so it would take a bunch of terms to get down to -0.51, say. So because it's getting closer and closer, more slowly and slowly. Okay, so that's what you got there. It does seem to be that's going to -1/2, and that's what this tells you. Much faster and easier than doing that. All right, now I think I'm going to clear this screen out of the way because it might take longer to do the next one. Here's the next sequence. This is example 4. Show that the sequence whose nth term is a sub n. What did I do with? There it is. Okay. Goodness, it's hot in here today. A sub n is equal to n squared over 2 to the nth minus 1. Okay, now that is not going to have an easy way of doing. If those are all polynomials like the last one was, then the technique we did before, divide by, in this case, n squared. But the denominator doesn't have a polynomial in it. It has an exponential function in it. So polynomials, exponentials, those are different functions, so you can't treat them the same. But what we do here is consider the function f of x, okay, and f of x would then be x squared over 2 to the x minus 1. That's what it means to change it to a function. Now we want to take the limit of that. The limit as x is approaching infinity of x squared over 2 to the x minus 1. All right. Now, it just so happens my Cal 1 class has just been introducing this. What if you have an expression that's infinity over infinity? Because certainly x squared, as x goes to infinity, you square it, it gets enormously big. And 2 to the x, as x goes to infinity, that gets enormously big. Subtracting 1 is not going to make a lot of difference, but you know, which is winning? Who's winning? If the numerator is winning, it's going to infinity. If the denominator is winning, the odds are it's going to 0. Let's see. Well, what do you do when you have an infinity over infinity? Just like a 0 over 0, use good old L'Hopital's rule. That should equal the limit as x is going to infinity of, take the derivative of this, you get 2x, and take the derivative of this. Oh man, what is the derivative of an exponential? Does anyone remember? Okay, if you don't, if you go to the front inside cover of your book, not the very first page, that gives you your, woo, it may not be back here. I thought it was. Oh wait, yeah, it was. I'm sorry. Basic differentiation rules. Okay, and what we have here is the derivative of 2 to the x. And let's see if we can find that. That would be front cover of your book. That would be a to the u. Okay, 2 to the x. And that would be the log of 2. Whoops, I'm writing on the wrong screen again. Log of 2 times 2 to the x. Because the derivative of -1 is 0. Okay? Well, guess what? As x is going to infinity, that's going to infinity, that's going to infinity. Well, guess what? Still infinity over infinity is an indeterminate form. Do L'Hopital's rule again. The limit as x goes to infinity of the derivative of the numerator, this time it's just 2, the denominator, the derivative of the denominator is log 2 times log 2, so I'm going to call that log 2 squared times 2 to the x. And guess what? This is going to infinity, that's going to 2. And for some reason a bell rang. I don't know if I finally said something bright or, whoops, I went to the wrong thing. I went to go to that. Don't have anyone new coming in, so that's not it. And I don't know. I want to. Yes.
How did you get the log times 2 part again?
Okay. Okay. Do you happen to have your book?
No.
No, you don't. Okay. Well, then I'll just have to tell you what the rule is. I'll write it down for you. This is from the front inside cover of the book. And this is just the derivative. Let me see. There, I don't know what makes the noises, but anyway, it just made it again. Let me see if I can get here. Okay, here is the derivative of, whoa, here, d by dx of a to the x. I should move this to my lap. It's just so much harder to do. Okay, let me do this. I'm having to look backwards. Okay, here is the rule for taking derivative of an exponential function. I swear this thing is such a pain in the neck. Okay, you probably couldn't see all that, but it's a pain in the neck on my part. It is the derivative of a to the u, or a to the x. And there, I don't know what these noises are. Does anyone have a clue? Are people chatting with each other? Yeah, messages. Okay, that's fine. Y'all, that's perfectly fine. I'm trying to see if it's anything to me. Okay, here is the rule. Okay, log a, and this, it really doesn't answer your question, but this is what the rule is: a to the x. That's what the derivative of a to the x is. It's just log a times a to the x. That's it. I mean, that's just the rule. Now, it should remind you of d by dx of, here is a e to the x. E is just some number, a 2.71 blah 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 blah. We just did that not long ago. Anyone remember what that was? Well, according to this rule, that would be log of e, log of the base, times e to the x. But sure enough, log of e, because they're inverse functions of each other, that's just 1 e to the x. So yeah, we knew that. Derivative of e to the x is itself e to the x. Well, as long as the derivative of a to the x, it's a to the x. But the coefficient is log whatever your base is, the natural log of your base. If it's something less than e, like 2.7, it's going to be a slightly smaller number. If it's something greater than, like a is 3, then that's going to be a slightly bigger number. Okay, so because the log 3 is larger than 1. I don't know. I mean, I could take you through and do the definition of it, but it would probably be really, really complicated. That's the bottom line. That's how you take the derivative of a exponential function that's not based e. Okay, you just take the log of the base and then multiply it by itself, a to the x. That's just a rule, just like the derivative of x squared is 2x. I mean, you do it often enough, you don't think about where that came from, but it was a long, involved process to get there. But after you do it often enough, you don't care anymore. It's just 2x. This is what it is when it's anytime you're taking the log of an exponential function of a base other than e, it's the log of that base times the same exponential function. If it is base e, it's just log of it's just the same function, because log of e is 1. That's probably not a great answer, but will it do? Yeah. Okay. Now, let's look at what we've got down here. Down here, the limit of 2 is just 2. And the limit of this denominator is still going to infinity. And what is 2 over infinity? 0. So sure enough, this is going to 0. All right. So if anyone's trying to send me a message, let me know. Just speak up, because I have so many things open. Chats or things like this don't show up for me. Now, if you're just chatting among yourselves, that's fine. That's perfectly okay. But if it's anything you're trying to get to me, go on and say it. I want to hear it so everybody can hear it and we can deal with it. Just like Houston did that question. Okay, so that answer was 0. L'Hopital's rule, don't forget it. Okay. Now, then is where the top of 591 is where they introduce the factorial, and then, whoops, in the wrong thing. Let's go back to my slide set. Okay. 9.1. Here we are. And we'll go back to current slide, which was this one. Those were the properties. There was a factorial, and this was the example of that. And then this is the squeeze theorem. This is middle of page 591. Another useful limit theorem that can be rewritten for sequences is the squeeze theorem. I don't know if you remember that. They claim, well, no, they don't give you where this was. It was back in 2.3, section 2.3. You go back to get squeeze theorem, back when you were doing derivatives. And here's what it is for sequences. If the limit as n approaches infinity of a sub n, if it does have a limit, and that's also the limit as n approaches infinity of b sub n. So these two sequences have the same limits as n is going to infinity. Then there does exist some number n, capital N, such that for every a sub n less than some c sub n less than b sub n, okay, now here's the assumption here. The assumption here is b sub n must be greater than a sub n. They didn't say that here, but that's what they're implying here. okay, because C sub n has to be in between A sub n and B sub n. There exists some integer capital N such that for any A sub n less than C sub n less than B sub n, for all n's greater than that n that we chose here, that big N here, then the limit of C sub n also has to be L. Because if C is in between A and B, and the limit for A is L, and the limit for B is L, the limit for C's got to be L. I mean, it's just that straightforward. They can really mess it up by putting all these ifs, then, and else's in there, but that's what it comes down to. Okay? So here's example 5, and that is the one given in the book next. Excuse me. Sorry. Show that the sequence C sub n is, and here's what C sub n is defined to be, minus 1 over 1 over n factorial. Minus 1 to the nth over n factorial. Show that it converges and find its limit. Okay. And I think I know what they want you to use. But let's just follow what they are going to say, okay? To apply the squeeze theorem, you must find two convergent sequences that can be related to that sequence, okay? And the first one of these would be, here are two possibilities. You can use others. A sub n could be negative 1, there it is, negative 1 over 2 sub n, and B sub n could be positive 1 over 2 sub n, 2 to the n. Okay? And you know both of these have to converge to 0 because the numerator is fixed, negative 1 and positive 1. The denominator gets big without bound and just keeps getting bigger and bigger and bigger. They're the same denominator, so they do. So you got a one approaching 0 from the bottom side and one approaching 0 from the top side. So both of those limits are 0. Now, here's what they're saying. This C sub n up here, because it's negative 1 to the n, when n is odd, that's always going to be minus 1. When n is even, that's always going to be plus 1. So this would either be 1 over n factorial or negative 1 over n factorial or positive 1 over n factorial. Okay? Now, if you think about that too heavily, you say, well, my goodness, n factorial is going to be getting bigger and bigger and bigger. So there's a negative 1 over a very big number. That's going to 0 from the underneath side. And positive 1, when you have a plus 1 there, you're approaching n factorial, or you're approaching 0 from the upper side. So yeah, that's got to be 0. But using these two that they claim you already know are going to be converging to 0, all you have to do is show that this one is in between that and that for all values for n. So that's what they're going to try to show by comparing the terms n factorial to 2 to the n. You can see that n factorial would be 1 times 2 times 3 times 4 times 5 times 6 all the way up to n. Whereas 2 to the n is going to be 2 times 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 2 up to 2 to the n. Okay? I mean, that's going to be the last one. Whatever n is, that's how many 2's you have. Well, just looking at this, this 2, let me do it this way. This 2 and that 2 could divide out, especially if you did the ratio of these. Okay? And these two could divide out there, and then every number up here, 3 times 5 times 6 times 7 times 8 times 9, are greater than 2 times 2 times 2 times 2 times 2. So what you have left over, the n factorial is always way bigger, way bigger than 2 to the n. Anything past 4, okay, when n greater than or equal to 4, these things are so much bigger. When n is equal to 4, n factorial is 16, 2 to the n is 24, 2 to the n is 16. Okay, make sure nobody is trying to come in. I don't think they are, but I can't get, oh, I know. If I hold, okay, no, we got all 6 people here. Okay. I can't just go by how many people are here because someone could have checked out and someone else trying to come, or the same person trying to come back in. So I have to always check. Okay. So anytime n is greater than 4, when n is equal to 4, n factorial is 24, 2 to the n is 16, and then you're multiplying this next by so many factors. Every one of these factors is bigger than that factor. I mean, by a large amount. More than doubled here, more than exactly tripled here, and they just keep getting bigger and bigger and bigger. So this one's greater than that, so this has to be 1 over that has to be less than either of those, and it is. Okay, now whether you can tell that's a squeeze theorem or not, that's what it is. This implies that for any n greater than or equal to 4, that was our capital N before, 2 to the n is always less than n factorial. So negative 1 over 2 to n is always going to be less than or equal to negative 1 to the n over n factorial, and that's less than or equal to 1 over 2 to the n. And if both of these converge to 0, that means that one has to. And sure enough, it does. At the beginning, no. Okay, it's outside. But after you get past 4, 1, 2, 3, 4, after that, you're inside of that envelope. Now, it gets so close you can't tell, but you are. You're always inside the envelope. Okay. Again, this is a little abstract, but if you try to use the logic like this, you'll see that it works. Okay, so by the squeeze theorem, then obviously if both of the other two, the two on the outside, this one and this one are both going to 0, this one on the inside has to go to 0 too. All right, before I do this, I've got to get something else to drink. My throat's getting dry. Sorry about that. All right. That was example 5. It's given in the book also. Now, here is theorem 9.4, top of page 592. The absolute value theorem. If you have a sequence, a sub n, and if that the limit as n goes to infinity of the absolute value of a sub n, which by the way means every one of those entries has to be positive. Okay? By itself, a sub n, they could be alternating plus minus plus minus plus. Where is it here? Come on, show up somewhere. There it is. Okay. These could be alternating plus minus plus minus plus, but if the absolute value of that, those are always positive. If that limit is 0 when they're all positive, then if they're alternating but getting closer to 0, which says this is, then that one has to be. So the absolute value theorem, if you can show that the absolute value of a sequence is going to 0, that guarantees the sequence is going to 0. Okay? Now the reverse is not necessarily true. Just because a sequence goes to 0 doesn't guarantee its absolute value does. But if the absolute value does, you guaranteed that the sequence will. Whoa. Oh no. The next is pattern recognition for sequences. This is in your book this way too. There is a proof underneath the absolute value theorem. I'll let you look at that. We just don't really have time for the proofs. We got to move. Here's pattern recognition. Sometimes the terms of a sequence are generated by some rule that does not explicitly identify the nth term of the sequence. Yeah, we're going to run into those. In fact, we really have already run into them. We just didn't point them out. In such cases, you may be required to discover a pattern in the sequence and to describe the nth term. You may not be able to define it with an algebraic expression, but you may be able to describe it once you found the pattern. Once the nth term has been specified, then you can investigate the consequence, the convergence or the divergence of that sequence. Now that's a lot of blah blah blah. Excuse me. Here's a sequence A sub n whose first 5 terms are 2 over 1, 4 over 3, 8 over 5, 16 over 7, 32 over 9. Okay? Now, just looking at that, it looks like to me this is 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, over the odd numbers 1, 3, 5, 7, 9. Well, you could express this as 2n minus 1 when n is equal to 1. That would be 2n minus 1. This is 2n minus 1 when n is equal to 2. That would be 4 minus 1 is 3. When n is 3, that would be 6 minus 1 is 7. So 2n minus 1. Okay, well that one you could come up with a sub n. Okay, it looks like to me that a sub n would equal 2 to the nth over 2n minus 1. Now that's what it looks like it is to me. Now, what we're asked to do is determine whether the sequence that we've chosen here converges or diverges. Well, looking at this, this is 2 here. This is 1 1/3. That is 1 3/5. So that's gotten a little bigger than 1 1/3. This would be 2 2/7. This would be 3 5 whatever. Okay, so yeah, that looks like that diverges to me. Okay, and looking at this, this gets bigger way faster than the denominator does. Okay, well therefore this looks like that has to diverge. Let's see how they do it. First, note that the numerators are successive powers of 2. The denominators form a sequence of positive odd integers. That's exactly what we noted. Okay, by comparing a to n, a sub n with n, you get this pattern, 2 to the n, just like we did, over 2n minus 1. Okay, now consider the function of real variable that would be this. Okay, so we'll go back to L'Hopital's rule. So let's go back and do that. Okay, we'll look at the function f of x rather than a sub n would be 2 to the x over 2x minus 1. And we want to take the limit of that as n goes to infinity of 2 to the x over 2x minus 1. Okay, now as x going to infinity, that gets infinitely large. As x going to infinity, that gets infinitely large. Who's winning? Well, it looks like to me that one's going to outpace this one big time. But let's take a look and see. Okay, let's do L'Hopital's rule, and that says that that would be the same as the limit as n approaches infinity of, take the derivative of this, remember that one? We just had it, log 2 times 2 to the x. log of the base times the function itself. Divided by the derivative of this is just 2. Well, guess what? This is an infinite number divided by 2. That's going infinitely large. No way around it. But looking at these, it's got to. Looking at these, it's got to. I mean, you're getting bigger and bigger and bigger. Now, the first two don't. From here to here, it gets smaller, just by a little bit. But then it gets bigger, 1.6, 2 point whatever, 2 and 2/7, 3 and 5/9. I bet you the next one's going to be 4 or greater. So that's just getting bigger and bigger and bigger. No way that's going to converge. Okay? So consider a function of that real variable, apply L'Hopital's rule, and you get 2 to the x times log 2 divided by 2. That's infinite. No longer infinity over infinity. That's just infinity over a number. So that's infinitely large. Not going to converge. Now, why in the world would you need to apply Theorem 9.1? Seems like it's intuitively obvious, but what it says here, it just says apply it. The absolute value theorem. I don't see any absolute, oh wait, I'm sorry, 9.1, I'm sorry, I was looking at 9.4. 9.1 said, well actually it doesn't really address it at all, but yes, it converges, it diverges big time. Alright, now we're going to look at another with a very funny name. Oh wait, before we do that, here's example 7. Now, I don't know why they say you don't have a rule, you had a rule. Example 7, finding the nth term of a sequence. Okay, let me get my whiteboard up again. How are we doing on time? We go to 1:55. Okay. Now, all right, to clear this, it's the one we did earlier. All right, here's example 7. Determine the nth term of this sequence whose first 5 terms are -2/1, strange number, 8/2, -26/6, 80/24, and -242 over 120. Weird sequence. Okay. Now we got to figure out what in the world is going on here. I can look at those denominators and recognize that's n factorial. 1 factorial is 1, 2 factorial is 2, 3 factorial is 3 times 2, that's 6, 4 factorial is 4 times 6 is 24, 5 factorial is 24 times 5, which is 120. So we got the denominator, okay? That would be n factorial. Okay. The numerator, I'll tell you the first part of it. It's -1 to the nth power. That changes signs every other time. The first sign is negative, the second is positive, the third is negative. So that's what gives you that part. Now what we got to do is figure out where in the world do we get this 2, 8, 26, 80, 242. Weird. Okay. Well, one thing I notice is that every one has a 2 in it. So let's factor out a 2 to begin with. And then what we have left is 1, 4, 13, 40, and 1, I'm not messing around with signs right now, 121. That didn't help me a lot at all. I don't know if it gave you any satisfaction. It sure didn't help me much. What is the relationship between these numbers? Okay. Wow. Three of those numbers are perfect squares, but 2 of them are not. So squaring doesn't seem to help any here. Does anyone see a pattern? And let's just put our ends down here. This is n equal 1, 2, 3, 4, 5. Okay. Okay. I thought I heard my phone ringing, but it's just a message that I can't make out, so I don't care. 5 cubed is 125. 4 cubed is 64. 3 cubed is 27. 4 cubed is 2 cubed is 8. Trying to see if cubes could come into play here. I don't really see how, but maybe they do. Well, let's not waste any more class time in it. Let's let them show us the magic here. Okay. That's it. I was getting close, but not quite there. Okay. 1 to the first power okay. Forget what I was doing here. So I'm going to erase. I don't know if it will erase. Let me see if it will. This morning it started not erasing, and it hasn't started back again yet. So let's just ignore this for now. Okay, here it goes again. I don't know. Some ridiculous looking message. I don't care what it is. Okay. So, 3 to the first power is 3, and then subtract 1 from it and you get 2. 3 to the second power is 9, and subtract 1 from it and you get 8. 3 to the third power is 27. subtract 1 from it, and you get 26. 3 to the 4th power is 81. Subtract 1, you get 80. Oh, there it is. Strange one. 3 to the n minus 1. That's your numerator. It would take me a long time to get that one out, because I don't, now that I think about it, 3 to the 5th power is 243. Nowhere close to that. But the others should have been sort of a clue. 3 to the 1st is 3. We got a 2. 3 to the 2nd is a 9. That's a 8. 3 to the 3rd is 27. Yeah. So that's our pattern. There's our A sub n. Sometimes they're not very easy to do. Sometimes they're incredibly hard to do. Now the question is, I don't know if they're going to ask the question, then decide whether that converges or diverges. Okay. Well, what we'd have to do is consider the absolute value of this. The absolute value of this is just going to let us throw away this one. So then let's look at the limit as x approaches infinity of 3 to the x minus 1 over x factorial. Uh-oh. I don't think we can do that, because there is no such thing as x factorial. So that's out of the question on this one. Okay. But we ask ourselves, who wins here? Sort of like we did before. 3 to the n is 3 times 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 dot 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 times 3. Okay. n factorial is 1 times 2 times 3 times 4 times 5 times 6 times 7 times dot 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 times n. Okay. Now you look at these. Okay. 3 times 3, 3 over 3, that will go away. 3 times 3 is 9. So somewhere up here you got a 9. Okay. So wipe that one out. Okay. And then the rest of these, this is less than that, that's less than that, that's less than that, that's less than that. Even with that gone, you know, it's less than, less than. So that numerator is way, way, way less than the denominator. So this is going to 0. Wait. Yeah. This is going to 0. It takes a long time to get there. This is a minus 2, a plus 4, a minus 4 point something. Then this becomes less than 4. This becomes less than 2, or just a little over 2. And after a while then, sure enough, the numerators are dropping off faster than the denominators are increasing big time. So this wins. Oh, here comes James. Now that means he must have got kicked out and brought back in, because I already had him here. Yep, already had him here today. Welcome back, James. So that one will converge. Did they say what it converges? Oh, and it converges to 0, because the denominator gets large way, way faster than the numerator. Absolutely, and if it does absolutely, then it's guaranteed to converge. The sequence converges. That's not absolute. Okay, that's from 9.4. All right, now we're finally through with that, and let's go back to our slide set. And we've got 4 minutes. Is that right? How time flies when you're having fun. Okay, 9.1. Okay, go back to current slide. And this is monotonic sequences and bounded sequences. Okay, so I think we're going to run out of time before we get this, but let's at least get started on it. Let me bring my phone down. Well, I can use my wristwatch. Okay. Here's what we mean by a monotonic series. And you see the term mono, that means one. And what that means here is going in one direction, either constantly increasing or constantly decreasing. That's what we mean by monotonic. Something that's jig-jagging like that, not monotonic. Monotonic is consistently decreasing or consistently increasing. So a sequence A sub n is monotonic when its terms are non-decreasing or non-increasing. Now they say it slightly differently from what I said. Okay? I said consistently decreasing or consistently increasing. Consistently increasing would be non-decreasing, okay? Which means they can't go up and level out, up and level out. That's not consistently non-decreasing. That is sometimes equal, okay? This is consistently increasing. In other words, A sub 1 is always less than A sub 2, less than or equal to. So I'm sorry, this does include a no change in it, whereas consistently increasing would not. This is consistently non-decreasing, meaning it can have those plateaus in between and still be consistently non-decreasing. So A sub 1 is less than or equal to A sub 2 is less than or equal to A sub 3 is less than or equal to A sub n, and that's always less than or equal to whatever the next one is. Or when its terms are non-increasing, which means they could be, okay, non-increasing, that means they're not going up, but they could be leveling out. So I think I said the other one backwards. A sub 1 is greater than or equal to A sub 2 is greater than or equal to A sub 3 is greater than or equal to A sub 4 is greater than or equal to A sub n. That's greater than or equal to A sub 1. So these are either decreasing or staying steady, just not increasing. These up here are increasing or staying steady, but not decreasing. Okay. One more minute. Here is example 8, and I'm sure we're not going to have time for it. So let's stop right here, say that's where we're going to pick out next time. Example 8 on page 594. And let me give you homework exercises. We're just within that much of finishing 9-1. Okay? Those concept checks at the top of page 191, good to look at. Okay? Homework exercises, any of the odds 5 through 9, they're all at Calc Chat. 9's at Calc View. 11's at Calc Chat. 13 or 15 are both at Calc Chat. You might be able to do all 4 of those. It's just matching the figures with the formulas, but at least 13 and 15 will have the answers in the back and at Calc Chat. 17 or 19 are both at Calc Chat. 21 or 23 are both at Calc Chat. 21's at Calc View. 25 and 27 are both at Calc Chat. Any of the odds 29 to 43 should all be at Calc Chat. 29's at Calc View. 45 through 51 should all be at Calc Chat. 49's at Calc View. And then stop there because we haven't done the monotonic. So go through 52. Any questions? Any whatsoever? All right. I'm going to stop sharing then. I'm sick and tired of sharing. Now, question. Any last thoughts, parting shots, anything before I end the meeting for all of us? I don't hear anything, so you take care of yourselves. Everybody wipe off your microphone. No, I'm just kidding. Let's end the meeting, and we will pick up again on Wednesday. Okay? Take care. Bye-bye.